So now let's talk about what to do in a case where our characteristic polynomial has repeated roots. So recall what we're doing is we're solving this differential equation, y double prime plus ay prime plus by equals 0. And our guess for the solution was e to the rt exponential. And we found that if we take the derivative, second derivative, plug it into this differential equation, we get our characteristic polynomial. So we're calling it characteristic polynomial. And it's a polynomial in R squared plus AR plus B equals 0. And we've talked about what to do in a case where we have two real roots to this characteristic polynomial, and also in the case where we have a pair of complex roots, complex conjugate roots. But there's one other case. We could actually have a quadratic equation here that just has one root. And that one root could happen with, one root will happen with multiplicity 2. So just an example of this. R squared plus 4r plus 4. This quadratic here, so that equals 0. That has a single root, because we can factor this as r plus 2 times r plus 2, so r plus 2 squared. And so our root is -2, but that's our only root. We don't have another one. See, it appears twice here in the factorization. Okay. Well, what do we know? We know that e to the rt is going to be a solution. However, we don't have a second solution. We don't have a second solution that's not just a constant multiple of this one. And that's a problem. So let's talk about what to do. Because remember, to form the general solution, we need two linearly independent solutions. Okay. Well, first of all, let's figure out exactly when something like this will have just one root. And you might remember how this works. So if we just write out the quadratic formula, so it's b negative b, which is actually negative capital A here, plus or minus the square root of a squared minus 4b over 2. Okay, so I'm just using the quadratic formula. Well, when will this have one real root? It will have one real root when this thing inside the square root is 0. So this has one real root. When does it have one real root? It's when this a squared minus 4b equals 0. Okay. And I think we talked about this in a previous lecture, but this thing right here is called the discriminant of the quadratic polynomial, and that's denoted by this capital delta. So when the discriminant is 0, we have one real root. And what is that root? It's just negative a over 2. Okay. And as we said, e to the rt is going to be a solution. So then, here's one solution. E to the rt is a solution. Okay. But to form the general solution, we're going to need another solution that's not just a constant multiple of this one, okay? So how do we find that? So here's one way to do it. We're going to just guess a second solution that's not just a constant multiple of this one. So maybe it's some other function. I'll call that u of t for now, times e to the rt. And it turns out it's actually important that I include this first solution in my guess, or else this method isn't going to work. So we're going to guess this, but with the stipulation that u of t is not a constant. Not a constant. Constant, okay? Okay. Well, now what are we going to do with this? Going to do the natural thing and just plug it into the differential equation and then see if we can deduce what this function u is. Okay. Well, let's take the derivative. So it's the product rule, right? U of t is some function of t, so it's u prime e to the rt plus u r e to the rt by the product rule. And then we have u double prime, or sorry, y double prime is, well, we have to use the product rule twice here. So u double prime e to the rt. Then we have plus an r, sorry. Yeah, that's right. A u prime r e to the rt. Okay, and then we have plus. Here we get another u prime r e to the rt, actually. So let's put a 2 there, right? So we actually get this same term from both of these. And then what's the other term here? It's taking the derivative of this part. So we get u r squared e to the rt. Okay. So that's using the product rule. And now we're just going to plug this into our differential equation. It's going to look kind of complicated. Here's our differential equation. Okay, so this is my y double prime. Might want to speed this video up here. E to the rt plus u r squared e to the rt. And then we have plus a times y prime. U prime e to the rt plus u r e to the rt. Plus b times just this one here. So notice I'm abbreviating u of t. I'm just calling that u. But u is a function of t. B u e to the rt. And this is, well, we want this to equal 0. We want to choose u so that this is a true statement here. So can we do that, I guess is the question. And this is a mess, but we notice there's an e to the rt in every term, so let's cancel that out at least. Cancel out all the e to the rt's. And then I think what I want to do is I want to rewrite this. So we have the u double primes together. There's only that one. And then I want the u prime terms. So let's see, there are 2 of those. There's this one and this one. So I have a 2r plus a times u prime, right? And then I want the u terms. So it's that one, and that one. So what are the coefficients? This one has an r squared. This one here has a ar. This is looking a little familiar. And then this one has a b times u. And that's going to equal 0. Okay. Well, does this help us is the question, right? We now have another second order differential equation, different than the one we started with, that we have to solve for u. But it turns out this is a super easy second order differential equation, and that's because what is r squared plus ar plus b? What is r? R is this part of the solution that came from taking a root of this polynomial, right? So r is a root of this polynomial, which means this is just 0. So this term goes away completely. And then what about 2r plus a? Do you see what that is going to be? Well, what was our formula for the root? It was negative a over 2, right? So 2r plus a is also 0. So this is also 0. So what do we end up with? We end up with u double prime is 0. So that simplified quite a bit. And this is a differential equation that's we could have solved on the first day almost, right? You can just solve it by taking antiderivatives. So if u double prime is 0, well, what's u prime? It's a constant. And then what is u? Well, it's c1t plus c2. Right? Okay. Very cool. Okay, so we have u is this linear function here. Let's recall what we were trying to do. We were trying to find u of t so that we get a second solution here. But with the added stipulation that u of t is not a constant. So remember, all we need is one u of t. This actually gives us a lot of u of t's. We can choose c1 and c2. We just need to be careful to choose c1 and c2 so that we don't just get a constant. So in other words, I want this t term to show up. So I want to choose c1 so it's not it's not 0. Right? So let's just choose u of t to be, why don't we choose c1 to be 1 and we'll choose c2 to be 0. So in other words, just choose the function t. Okay. Then y2 of t is t e to the rt. And what do we know? We know that this is a solution. And in particular, it's not just a constant multiple of this one. So it's a second linearly independent solution. Okay. So the general solution, I'm going to just write it down now, is what? General solution is going to look like c1 e to the rt, where again r is just the one root of this characteristic polynomial, plus, and look what we need to do for the second one. We have c2 t e to the rt. Okay. So we get this, exponential function times a linear function. It's the same r up here, right? So this is our general solution in this repeated roots case. And with that, we're done solving this differential equation. So we've looked at all three cases. In all three cases, we get something slightly different. So let's summarize. So maybe not even slightly different. Something that's significantly different. So solution to, just remember we got sines and cosines appearing when we had imaginary roots. So solution to y double prime plus ay prime plus by equals 0. Let's just summarize what we found. Well, what was the idea? The main idea was to guess an exponential function, rt, and then we plug it in, and we obtain a polynomial in R that we're calling the characteristic polynomial. Okay, and what was our characteristic polynomial? It looked like r squared plus ar plus b equals 0. And we had three cases. So let's write the three cases. I think I have room for that. So case 1, case 2, and case 3. So case 1, what was case 1? 2 real roots. And let's call them R1 and R2. Okay. In that case, the general solution, this was the easiest case to write down a general solution. The general solution just turned out to be, we could just use those 2 roots. So C1 e to the R1t plus C2 e to the R2t. What about case 2? Case 2, where we had two complex roots. And recall that we could write those complex roots as, if one of them was a plus bi, the other one would be a minus bi. Okay? So they were complex conjugates of one another. And in that case, our general solution was, it involves sines and cosines. So what did we do? We took this, we just plugged it in there, but then we had to take real and imaginary parts of that complex function. And remember, the idea was to use Euler's formula to do that. And so that's where the sines and the cosines come from. And we ended up with C1 e to the AT cosine BT plus C2 e to the AT sine BT. Okay, and then in case 3 we just did today. So that's the case where we have one repeated real root. You can't have one repeated complex root. If you have one repeated root, it has to be real. So we really are looking at all the cases, all the possible cases. So we'll call that R. And then what did we just find today? We found that the general solution is C1 e to the R2 e to the RT plus C2 t e to the, I'll put in that t in another color just to emphasize it. So that's a little unusual. C2 t e to the RT. Okay. Really this is probably the most important information from the previous 3 or 4 lectures. If you're just interested in solving these, you don't even care, where these solutions come from. You can just remember what we have here. It's important to know where this comes from, though, because you might have to solve slightly different looking differential equations, and you'll have to basically adapt the method that we use to a new situation. Okay. So I just want to point out one thing. I just want to emphasize one thing that's really important. So what is actually determining which case we're in? What's determining the form of the solutions? So yeah, it's really important. So the form of the solutions there's actually just one number you can look at, and then you know what case you're in. So the form of the solutions is determined by the roots of the characteristic polynomial, and what determines, whether we have 2 real roots, 2 complex roots, or 1 repeated real root for a quadratic equation? It's that discriminant. It's this discriminant that we saw. So in particular, the discriminant of the quadratic equation. Discriminant is just one number you can look at, and that tells you what case you're in. So it's very cool. And so, yeah, what is our discriminant? In our case, it's if we have y double prime plus ay prime plus b, it's just a squared minus 4b. So we look at the discriminant, and if the discriminant is positive, okay, then this thing inside the square root is going to be positive. So we're going to get real solutions. It's not going to be 0, right? So we actually get 2 distinct real solutions that come from the plus and the minus. So if the discriminant is positive, then we are in case 1. And if the discriminant is negative, well, then we have a negative under the square root. That's going to be complex roots, so we have case 2. And finally, if the discriminant is exactly 0, that's when we're in case 3. Case 3 is sort of like the boundary case between, yeah, this case here and this case here. Okay. And you'll see also like the name characteristic polynomial. That's a very fitting name because that polynomial, just this one polynomial here and its discriminant, completely characterizes the behavior of the solutions, okay, into these three categories. All right, great. So if I end this lecture now, I think that'll be a little bit short, but we're done talking about solving this differential equation. But what I'd like to do is I'd like to point out that this method that we used to generate a second solution is actually a very general method. And we can use it in many cases when we have a single solution to a linear homogeneous differential equation and we need to find another one. And so in general, this method is called, so we're done with this, but in general, this method is called the reduction of order. We'll see why it's called reduction of order in a second. Okay. So underline that. Okay, so what is reduction of order? It's a method to find a second solution when we have one. So a second linearly independent solution. To a linear, so it has to be linear. It doesn't have to have constant coefficients. So this is a pretty general method. But it does have to be homogeneous. Linear homogeneous differential equation given we already know one. Okay. So let's say we're given a differential equation and we'll do y double prime plus p of t y prime plus q of t y equals 0 and a solution. Just one solution. We know one solution is not enough, right, to generate the general solution. So what do? We basically do the same thing that we did here. So we're going to guess a second solution that's not a constant multiple of this one. So it's maybe the first one, we're going to actually use the first one in our guess, but then we're going to multiply by some unknown function u of t, and then we're going to insist that that function is not a constant. Okay, so we guess a second solution of the form y2 is some unknown function u of t times our first known solution, right? And we want u of t to be not a constant, okay, so a non-constant function. Okay, and then the idea is we just plug this into the differential equation. Equation. And what happened in our other case when we did this, we actually obtained a simpler differential equation. And that seemed kind of amazing in that example that we got such a simple differential equation, but it turns out this is always going to happen. And it won't quite be as simple as u double prime equals 0. But what's going to happen is the order is going to be reduced of that differential equation. And that's, hence the term reduction of order. So we're going to see how that happens. So we obtain a simpler, let's just say that, simpler differential equation that can be solved for u. Okay. The best way to see this is by doing an example. So I've constructed an example of this. So here's our example. I'm going to tell you one solution. So one solution to, and just for fun, let's do a differential equation that does not have constant coefficients. So x squared y double prime. Just want to use the independent variable x just to kind of change things up a little bit. And we have 2x times y prime minus 6y equals 0. So we don't have constant coefficients here, right? Our coefficients are some function of the independent variable. That's okay, it's still linear, right? Because we just have y double prime, y prime, and y. Okay, so one solution to this is x squared. So just the function y equals x squared. Given that information, I want us to find a general solution. So let's see if we can do that. Seems like we're given very little information in order to do that. And what's more, we don't know how to solve differential equations of this form. Because they don't have constant coefficients. So our usual guess, e to the rt, is not going to work. Right? Okay, so what's the idea? Our idea is to guess something of this form. So we're going to guess y2 is some unknown function u of x times x squared. And we're insisting that u of x is not a constant. Okay. Okay, let's take the derivative of this. So we get u prime times x squared plus 2ux, the product rule. And again, we're going to have to use product rule for second derivatives. So we have u double prime x squared. And then what do we have? Are we going to get the same thing where we can combine two terms here? I think so. So we have 2u prime x. And we also get a 2u prime x from this one. So we actually have a 4u prime x. And then what's the other term that comes from this one? It's just going to be a 2u. Okay. And then we plug this all into the differential equation. So x squared times this. So again, where you can speed up the video if you want. Plus 2u plus 2x times y prime plus, minus 6 times u times x squared. That equals 0. And again, we want to figure out what u of x is. Okay. And let's hope that this simplifies quite a bit, and I think it will. Okay, so let's take the u double prime term first. What's that going to be? Well, it's just going to be a x to the 4, right? U double prime. And then what about our u prime terms? So we have this one and we have this one. So 4x cubed u prime plus 2x cubed u prime. That's 6x cubed u prime. And then we finally have our u terms. So we have 2x squared u plus 4x squared u. Then we have minus 6x squared u. That cancels out, right? That just ends up with 0. So we just get this equals 0. And again, like I said, this is always going to happen. Right? We're always going to get something simpler. And notice that, so I mean, technically, I guess I'd still call this a second order differential equation, but there's an obvious substitution we can make where this will become a first order differential equation. Right? So after the substitution, you see what the substitution is? Instead of a first and second derivative, I'm just going to set v equal to u prime. So then this is v prime, right? U double prime is v prime. So after a substitution, v equals u prime, this becomes a first order differential equation. Very cool. First order differential equation. That's where this name comes from, reduction of order. So let's write what that first order differential equation is. So for v prime, right, as v is u prime, so if I take the derivative, I get v prime equals u double prime. And here we have 6x cubed times v equals 0. And now we have to remember how to solve these. So we're hoping this is linear and or separable, and it happens to be both, right? So this is linear and separable. So we can actually choose what method to use. So I already worked out the solution to this, but if you'd like, you can pause the video and try to solve this one. See if you remember how to solve first order differential equations. And so the solution ends up being C1 times x to the negative 6. We're going to say C. I'm putting C1 because I know there's going to be a C2 that comes up at some point. Okay. Well, let's try to remember what we were doing. So we just solved this problem within the problem, but we're after u of t, right? We're after, or u of x, right? We're after this u of x. Well, this is v, right? This is the derivative of u of x. So what is u of x? It's going to be the antiderivative of this. So we just get c1 x to the negative fifth. You know, I have a negative 1/5 out there technically, but you know, we can just rename this c1. That's fine. And then we have plus c2, right? This is just the arbitrary constant that comes from taking the antiderivative. So we have c1 and c2. Okay, so again, we just want to find some non-constant function u. We actually found a bunch of them. So let's just take one of them. So take, let's take u to be, which would be the simplest one to take. I suppose c1 should be 1, so we just get an x to the negative 5. And then c2 we might as well just take to be 0. Right? This is a non-constant function, so I definitely had to pick c1 to be something that's not 0. But c2 I can take to be 0. Okay, well if this is u of x, then what is our solution y2? It's u of x times, what is that, x squared. So my y2 is x to the negative fifth times x squared, which is x to the negative 3. So the general solution is something I can just write down now. Y of x is c1 times our first solution that we were just given. I guess we can take, right? X squared plus c2 times this new one that we found. And we're allowed to use that because it's linearly independent. And then, by what we talked about a few lectures ago, this is all the solutions. All the solutions can be obtained just from those two by taking these arbitrary constant multiples of them and adding them. It's true for any linear homogeneous differential equation, even if it doesn't have constant coefficients. Great. By the way, differential equations like this, they're called Euler equations. And you might notice with Euler equations, so the guess e to the RT doesn't work. Instead, it appears the guess that seems to be working here is x to a power, right? Or t to a power if t were independent variables. Let's conclude now, but I'll give you a problem to end with, so you can practice this reduction of order. So here's a problem you can try. Let's do a similar kind of thing. So one solution to, and I'll give you another Euler equation, x squared y double prime minus 3x y prime plus 4y equals 0. By the way, there are probably hundreds of things in mathematics that are named after Euler. So we've already seen Euler's method. We've seen Euler's formula. This is called an Euler equation. One solution to this is, so actually I think I worked this out so that x squared is again a solution. What I want you to do is find a general solution. And the idea is exactly the same as above, but there's a little bit of a twist that happens at the end here. And you actually end up getting something that's not just x to the r. You actually get a natural logarithm appearing, so be on the lookout for that. Okay, so that concludes this lecture, and that concludes our study of how to solve this equation.